This video is on electrode potentials. And the aims of this video are to understand how electrode potentials are measured using a standard hydrogen electrode, understand how to write half equations and full equations for redox reactions, and draw cells using conventional representation and calculate the EMF of a cell. So before we can understand how electrode potentials are measured, first we need to understand how a cell actually works. So what a cell basically is an equilibrium that is set up, two of them attached to each other. And if we just take, for example, copper in copper sulfate, so this is copper sulfate, so essentially Cu2+, this is a copper electrode, and on the other side we'll have, say, magnesium in magnesium sulfate, so Mg2+ and Mg. Now in both of these systems there's been an equilibrium set up, both on this side and on this side, and these equilibria are Cu in equilibrium with Cu2+ and 2 electrons, and Mg in equilibrium with Mg2+ and 2 electrons. Now how far to the right or left this equilibrium lies is determined by essentially how reactive the copper or magnesium is. So copper would essentially, in most cases, rather be copper metal than copper 2+, and so there's going to be very few electrons on this electrode here, because not many of the copper atoms, if you like, in this copper electrode have been given have turned into copper 2+, and therefore given up electrons that would reside on this metal. However, on the magnesium side, magnesium would much prefer, compared to copper, be magnesium 2+ rather than Mg. So there are far more electrons on this magnesium electrode than there are on this copper electrode. Now if we were to join these two electrodes together, say with a voltmeter, then what will happen is that the electrons on this electrode will flow through the voltmeter over onto this side, because this side is relatively more positive. Obviously both sides are negative, but it's relatively more positive than this side, and so the electrons will flow from the magnesium electrode to the copper electrode. And therefore the magnesium, if these two systems were set up, would be oxidized and lose electrons, and the copper would be reduced and gain electrons. The copper 2+ would be reduced and gain electrons. Now to complete this cell, if you like, we need to make sure the electrons or the charge can flow this way and then go back across. We need to complete the circuit, and we do that with something called a salt bridge. So we connect these with a salt bridge, which is made of an ionic substance, an ionic compound dissolved in water. For example, potassium nitrate is a good choice usually. Now for us to be able to predict reactions and which way the electrons will flow when two cells are connected together, we need to have a standard electrode that all of these are measured against. And when we connect those electrodes together with a voltmeter, the reading of that voltmeter will then be the electrode potential for that cell, which can then be compared to all the others because we have joined every cell up to a standard. And what that standard is the standard hydrogen electrode. So all of the numbers that you get in an exam, in these sorts of tables, these numbers here, these are all measurements that have been made against the standard hydrogen electrode. And in this slide I just want to show you what the standard hydrogen electrode is. You need to know the conditions, and you need to know the electrode and things like that. So the standard hydrogen electrode looks a little bit like this. So I'm just going to draw what would be a beaker. I imagine that when these are actually used, it's a little bit more high-tech than that. And we have acid with a platinum electrode dipped into it, and over that platinum electrode we pump hydrogen gas. So we have hydrogen gas going in here, pumped over the platinum electrode. And the reason why a platinum electrode is used is because platinum is pretty inert, it doesn't react, and it also conducts electricity. So if you're ever stuck for an electrode to use, so for example in these equations up here, the iron 2 plus and iron 3 plus electrode, there's no metal there, or solid metal, to conduct the electricity, so you'd need to use a platinum electrode to connect all that together. Go back to the hydrogen electrode. So we've got hydrogen gas going in, we've got acid down here, which must have a concentration of 1 mole per dm cubed of H plus ions. So that means you could have either 1 mole per dm cubed of HCl, or you could have 0.5 mole per dm cubed of sulfuric acid, and so on, because it's the H plus ions must be 1 mole per dm cubed. The hydrogen gas is at 100 kilopascals of pressure, and it must be at 298 Kelvin, and as I said before, you use platinum electrodes, or a platinum electrode. And once that's connected up to, say, the Fe2 plus Fe3 plus electrode, you will get an EMF value of plus 0.77, and so on for all of these. So the question is, how do we actually use the electrode potentials that are worked out by connecting these to the standard hydrogen electrode in an exam to work out what reaction will happen if we connect two of these electrodes together? So let's choose two of these electrodes to connect together. We'll choose the chlorine electrode, and we'll choose the iron 3, iron 2 plus electrode. So if we choose those two electrodes, we've got to look at the electrode potentials and look at which one's more negative and which one's more positive. So if we were to connect these two electrodes together, the 0.77 electrode, the iron 2 and the iron 3 electrode, is more negative relatively to the chlorine Cl- electrode. So if we were to connect these two together, the top one would be the negative electrode, the cathode, and the second one would be the positive electrode, or the anode. So the direction of electron flow will be from the negative electrode to the positive electrode, because that's the way the electrons are attracted. So the electrons will go from this electrode to this electrode, which means the top electrode is going to be losing electrons, because electrons are flowing away from it, and the bottom electrode is going to be gaining electrons, because electrons are flowing to it. Now if we look at the way all these are written, every single one of these equations is written with the electrons on the left-hand side, i.e. on the reactant side, and therefore they're all being written as if they are gaining electrons. So everything on this left-hand side is being reduced to make the stuff on the right-hand side. So the one that is gaining electrons in this reaction is the one that is the right way round. So this chlorine plus 2E minus to make 2Cl minus is the correct way round, because it is gaining electrons in this whole process. The top one, iron 3 plus plus electron to iron 2 plus, that is the wrong way round, because actually this equation needs to be losing electrons. So what we do is just switch that around, and so our two equations that we're going to add together will be iron 2 plus goes to make iron 3 plus and an electron, and Cl2 plus 2 electrons goes to make 2Cl minus. Now before we add these two things together, the electrons must cancel, and so we need to multiply the top electrode by 2, and then we add them together, and so what we'll get is Fe2 plus Cl2 goes to make 2Fe3 plus 2Cl minus. And that is what will happen when we connect those two equations together, those two half cells together. That's what will happen if they are discharging. If this was a rechargeable cell, then those then when it's being recharged, then that reaction will go the other way. But this is the spontaneous reaction that would happen if we connected those two cells together. So let's take the two electrodes that we were looking at in the previous slide. So that's the top one and the one below it. And let's say we'll connect them up. Now, if we would connect them up, then it would look a little bit like this. We'd have some sort of container to contain a mixture of iron 3 plus and iron 2 plus. We'd have an electrode which couldn't be made out of iron because that would affect the equilibrium of this iron 3 plus and iron 2 plus. It would need to be made out of something inert, which we said earlier would be platinum. We connect that through a voltmeter to platinum again, because this other electrode, the Cl minus and Cl2, neither of those will conduct electricity. We'll have Cl minus in here, and we'll have Cl2 being pumped over the top of that electrode, and then we connect it together with a salt bridge to complete the circuit. Now, if we were to do that, then the value that this voltmeter would show would be the difference between these two electrode potential values. So, and that is called the EMF. So the EMF value of this cell would equal 1.36 minus 0.77, i.e. the difference between them, which equals 0.59. Now if I put those two numbers the way around, I did 0.77 minus 1.36, then we get minus 0.59, and actually the difference between 0.59 and minus 0.59 is literally how I connect this voltmeter, either that way round or having these two the other way round. And whether it's 0.59 or minus 0.59 is determined by the polarity of the right-hand electrode. And what I mean by that is the right-hand electrode the positive electrode or the negative electrode? In this case, the chlorine electrode is the more positive one. So this side is the positive electrode and this side is the negative electrode. And so this is plus 0.59. But if I'd drawn this the other way around, then it would be minus 0.59 instead. Now this is a very cumbersome way of drawing this electrode. If I wanted to explain to another chemist how I'd set this electrode up, I wouldn't want to have to draw all this out. So instead we use something called a conventional representation of a cell. And to draw a cell, we just use certain symbols. So what we do is first we start off with the electrode that is in the cell. So in this case, it's platinum on this side. And then if there's a phase boundary, a change in state, so a phase boundary between the electrode and the solution it's in, which there will be because the electrode is a solid and the solution is aqueous, then we draw a straight line for a phase boundary. We then put in the solution, so Fe3 plus, and the Fe3 plus and the Fe2 plus are both in the solution, so we just draw a common between those. And then we'll draw the Cl minus, but that is connected by a salt bridge, and we represent the salt bridge by putting a double line between the one solution and the other solution. Then we draw the other solution, so it's going to be Cl minus, and then the Cl2 is a gas, so there's another phase boundary. I'm just going to change colour so you can actually see it. Sorry, I've squeezed this in too small a space. So Cl2, and then another phase boundary, and the PT. So if I just delete that and take another two cells to join together and do another example, let me just delete all that. So let's this time take the third electrode down and the last electrode. So in this case, again, we have no metal that will conduct the charge. So we've got BrO3 minus, we've got Br2. The H plus and the water are not taking part in the redox reaction that will go on. So we can kind of ignore those in terms of the cell representation. And we've got F2O on this side and F minus on this side. So neither of those conduct electricity. So we'd have PT first as the electrode. We then have a phase boundary. And which one of these we draw first will depend on what the EMF value is. So let's just pretend the EMF value is a negative value. And so we're going to put the more negative electrode on the right-hand side of this cell representation. So the more negative electrode is the bromine electrode, and the fluorine electrode or fluoride electrode is the more positive one. So we're going to draw the fluoride one first. So what we'll have is a phase boundary, and then you can see that F2O is a gas, so that's going to be pumped over the platinum. Then another phase boundary between F2O and the F- aqueous solution. Then the aqueous solution of F- is going to be connected to the aqueous solution of BrO3- and Br2. So by a salt bridge. So we've got a double line, then we have the Br2, BrO3- because they're both in the same phase, and then another line, and then the electrode which connecting these together. So that would be the cell representation of these two. So let's finish off with a few past exam questions. So in this question it says an electrochemical cell can be constructed using a zinc electrode and an electrode in which silver is in contact with silver oxide. This cell can be used to power electronic devices. Give the conventional representation for this cell. So we've got the zinc electrode up here, and we've got the silver oxide electrode here. Now, it doesn't tell you what the EMF is, so it doesn't actually matter in this case which way around we draw it. So we're going to start with the top one, and so it tells you that there's a zinc electrode involved. So we're not going to use platinum in this case, we're going to use zinc, so we're going to have zinc. And that's going to be separated by, there's a phase boundary between the zinc and the Zn2+. So one line, Zn2+. Then the salt bridge separates that from the Ag2O. And then the silver on the other side is your electrode. And it says calculate the EMF of the cell. Now, because we've drawn the cell representation, we can now calculate the EMF based on that. So the silver electrode is the one that's going to dictate the polarity of the EMF. And you can see the silver electrode is the more positive electrode, and the zinc electrode is the more negative one. So it's going to be a positive EMF, and the value is going to be 0.34 take away minus 0.76, which equals plus 1.1 volts. And it says, suggest one reason why the cell cannot be electronically recharged. If it ever asks you that question, it's because the reaction, or the cell reaction, is irreversible. The cell reaction has to be able to be reversed before it can be a rechargeable cell. And then this question asks you to describe a standard hydrogen electrode. Notice there's 4 marks, and there's 4 key points for a standard hydrogen electrode. Platinum electrodes, or electrode, sorry. 1 mole per dm cubed of H plus ions. If you'd written 1 mole per dm cubed of HCl or half mole per dm cubed of H2SO4, that would still get you the mark. Temperature of 298 Kelvin. And then H2 gas at 100 kilopascals. So the 4 main points you have to remember. And finally, this question says a conventional representation of a lithium cell is given below. This cell has an EMF of plus 2.91 volts. There it is. It says write a half equation for the reaction that occurs with the positive electrode of this cell. And it says calculate the standard electrode potential of this positive electrode. So the positive electrode of the cell is the right-hand cell, and it's going to show a conversion between these two things, or these 3 things, sorry, Li plus MnO2 and Li MnO2. So it could either be drawn this way, Li plus MnO2 plus an electron goes to make LiMnO2, or it could be drawn this way, LiMnO2 goes to make Li plus MnO2 plus an electron. Now the way it's written will depend on whether it's gaining or whether that cell is gaining or losing electrons. Now the fact it is the more positive electrode means it's going to be gaining electrons from the more negative one. So it must be this top one here, where it's gaining electrons. So we can discount this bottom one. And then it says calculate standard electrode potential of this positive electrode. So if the EMF is plus 2.91, and then we can look up the electrode potential of this cell here, which is this one here, minus 3.04, the difference between the electrode potential of the right-hand electrode and the electrode potential of the left-hand electrode has to be plus 2.91. and we've got to take into account the electrode potential of the left-hand electrode is minus 3.04. So either it could be minus 3.04 minus 2.91, which would give us minus 5.95, or it could be minus 3.04 plus 2.91, which would give me minus 0.13. Now, because we know this is the more positive electrode, it's going to be the number that is more positive than minus 3.04, which is this bottom number here. So we can discount this sum, make sure we scribble it out thoroughly so the examiner doesn't think that's one part of our answer, and those are our two answers there, and there.